Okay, good afternoon everybody. So we're gonna continue with our tutorial for molecular dynamics. This is the second part of the videos. I had no idea how many gonna be. It depends on my time that I have free and also on the content that people want me to discuss. But I mean, remember, this is for me a hobby and I do it for fun. But anyway, let's continue and see. So you remember on our last presentation, on our last video, I went into a summary that for doing molecular dynamics, we had to have the Newtonian equations, then we had to use a numerical integrator, and then we have the initial position, that velocities and acceleration. Then we can predict how the system is gonna behave. Okay, and if you remember, we also did an example, the three-body problem, and this is a way that how to define the interaction. Okay, and we went into discussing that if we have the potential energy of the system, we can find a force interaction by finding the gradient. Okay, and then we also make how we also run a simulation, and we look at the trajectory of the particles, in this case for three objects, and I discussed about adding an epsilon here in this equation, because remember that if we don't want the particles to come closer together too close, because if that happens, they're gonna be an error, because remember that when you have gravitational potential, if the distance becomes zero, then everything blows out. Okay, so we had to avoid that the distance between the objects becomes zero. One way to do it is by adding an epsilon here, adding a constant, but adding this epsilon changes the simulation completely. And also we discussed that when we're having an interaction, okay, for example, the gravitational potential, the simulation or the interaction is not gonna run forever, okay? So usually they're gonna be like an arc cut, a distance. When we define that from that distance forward, the interaction is gonna be zero. And that also are some things that we have to consider, because that is gonna change how the simulation behaves completely. And that's something that I was mentioning in the previous video and part number 1. But anyways, so what we had to know to do molecular dynamics. So this is a few things that you have to remember when you're working in molecular dynamics. More likely, this is something that you have already seen in college. You had taken a physics class, so I'm gonna go briefly into this. So you had to know what's a microstate, and microstate. You had to know what's the partition function, the derivation of thermodynamics laws by statistical mechanics, the idea of interaction. You had to go into a particle system, external environment, particle between a system of many particles. You had to define what's entropy, the equipartition theorem, temperature, and distributions like Maxwell, Boltzmann, Fermi, Dirac, or Bose-Einstein. I'm not gonna go into all this theory, okay, because that's not a purpose of these videos, okay. Probably I'm gonna explain this by doing examples and running some computer simulation on how to do MD. But I'm gonna go briefly into something really important, and that's the canonical ensemble. So pretty much when you're running molecular dynamics, remember that we have to have velocities, acceleration, forces, position of the atoms. Okay. Now the question becomes how we link these quantities that we have for molecular dynamics into the thermodynamic variables that we know, like pressure, volume, and temperature. Okay, so for doing that, we have the ensemble. So pretty much we have 1, 2, 3, 4. Okay, we have a microcanonical, That's when you have the number of particles, the volume, and the energy remains constant. We have the canonical. We have the number of particles, the volume, and the temperature. Okay, it remains constant. And we have the NPT. We have the pressure and temperature are under control. Now, which one we have to use? It depends on the simulation and it depends on the problem. The one that we have already been using, okay, and actually that's straightforward, implementing the Newton equation without any modification. That's when we are doing the tree problem, okay? And the only thing that we have to remember when doing molecular dynamics is that the energy of the system has to remain constant, okay? And that will be the scenario when you are in the microcanonical. Now, if you are in equilibrium, okay, then you have to go into NPT and NVT. Now, if you are doing non-equilibrium molecular dynamics, then you have to use a microcanonical. You have to use the NVE. And yes, because when you are in non-equilibrium, the temperature and the pressure are not gonna be the same. Yeah, they change over time. So, and there are some kind of simulation that you have to use the microcanonical, but that's not something we're gonna discuss in this video. Probably in another ones. But I want to remember I mentioned something important. The Newtonian equations remain the same or they are modified. When we are going into the canonical and we're going into the isothermal, isobaric ensembles, there are modifications to the Newtonian equations, okay? They're gonna be modifications. And just to give an example, when we go into the canonical ensemble, yes, the NVT, we have this equation right here. So we can see that this is pretty similar to Newtonian equations, okay? But we add in this coupling right here, yes, and this pretty much allows us to change the temperature of the system. Okie dokie, so we're back. So like I was saying before, when we're using the canonical and we're using the isothermal isobaric ensembles, there have to be modifications to the Newtonian equations like is right here in next slide. Okay, there are reasons for doing these modifications, but I'm not gonna go into that topic. And you only had to remember that there had to be modifications. Anyways, one of the problems that we have when we're doing molecular dynamics is to have the boundary conditions. So if you remember my last problem, when we defined the tree problem, there was no boundary conditions. I mean, the system was let to run. We are having to have a computational box, okay? But there are times like when we are, and actually I put here a video game, when we want the particle to be under, certain constraints. The same happened, for example, in quantum mechanics, where we had a particle inside a box. We define an infinite potentials on the left and on the right, and then we let a particle inside to move around, so the particle bounces back and forward. And it becomes more complicated when we are in two particles. And when we're doing 3, 4, 5 particles, it's going to become a little more complicated because you have to consider the interaction between the particles and the interaction between the boundaries. There are many things that happens when you're making okay, so there are many things that happens when you're having boundary conditions that the particle bounces back. Because if you remember, let's give you an example. So if you remember from thermostatic mechanics, the pressure can be defined as the number of particles that collides the surface. Okay, and when the particle going to the surface, it's gonna be an elastic collision. It's gonna be an elastic collision. It's gonna be how it's gonna be the transfer of energy, the transfer of momentum. Okay, so there are many surface effects that we have to consider. Okay, so there are two ways that we can remove the surface effects, and I'm gonna go into the next slide and define it. So the first thing that we have to consider, do we need boundary conditions? No, we don't have to have computational bugs. Just let the simulation run, okay, and the particles are free to move to whatever they want. Okay, the only problem is that when you're having no boundary conditions, if the interaction is not good enough, the particle can go away and never come back. Okay, so in that case, the simulation gonna crash. Okay, now also if you make computational bugs, okay, and you make the conventional bugs on particles to collide, there are gonna be a lot of surface effects. So another alternative that people do, it's they have periodic boundary conditions. So in periodic boundary conditions, you define your computational bugs, but you let the particle to go and transfer the surface, and then it comes back inside. Okay, so in that case, you don't have collisions with computational bugs. Okay, periodic boundary conditions are really good when you are working with crystals. Okay, they have periodic, they have asymmetry that it repeats itself. But if you're working with molecules, or you are working with nanoclusters, then periodic boundary conditions are not ideal. Okay, but if you are working with crystals, periodic boundary conditions is a really good way to remove surface effects. Okay, and that's something that we use, and that's something I'm gonna use for the simulation. I'm gonna continue showing you in the next presentations. And so yeah, remember, yes, try to use periodic boundary conditions when you are working with crystals. If you're working with proteins, molecules, something that's not periodic boundary conditions are not a good thing to use. What are the few things that we do incorrectly when we're doing molecular dynamics? The first thing that we do is that sometimes we put the atoms too close together. Okay, so if they are too close together and you run a simulation, then probably everything is gonna blow out. Okay. Another thing that we give realistic initial velocities. Okay, and also we want the particles to behave given certain rules of motion for, and I go back to this presentation here. Okay, that's something important because I'm going to define which ensemble we use. And then finally, you have to be careful when we define the surface effects. Okay, so having that in mind, I think that we are ready to run a computer simulation. So why we care about doing molecular dynamics? Okay, so basically I'm gonna give you an example. We want to find the melting temperature of copper. Okay, and that has to be at atmospheric pressure. We already know for experiment that the melting temperature is around 1358 Kelvin or 1084 Celsius. Okay, and we want to predict this. Sometimes when we are, and that's a really good video online to explain this, sometimes when we are doing experiments and we want, for example, to find how material expands or how the gas expands, can be really expensive and also it can give you a lot of danger. Okay, many things can happen and things can blow up and everything is out of control. So we can use molecular dynamics and try to predict things about the behavior of the materials without having to do experiments. It's wonderful because number one, experiments are really expensive, and also there are many things that may happen wrong when you do an experiment. So at least if we use a computer simulation and we have an idea what we can do before actually doing experiment, give us confidence that we're doing things right. But anyways, so I'm gonna go into this example right here, and we're gonna run a simulation of this. So I already have it right here. So I'm gonna use a computer software probably that everybody knows that's called LAMMPS. I already have it right here installed on my computer. You can see right here it's running, and this is the date of the version I'm using right now. And I have here my script. It's for mercury copper. So I'm gonna go briefly into this script and explain everything. So the first thing that we have to understand is the condition, the boundary condition. In this case, is gonna be periodic because we are running a crystalline structure. So using periodic boundary conditions is fine. Then we have to define variables. In this case, we define the initial temperature, we define the final temperature, and then we had to define a time step. And the time step that you use depends on the material that we're using, but typically it's in the picosecond range. Okay, that's the reason because when you're doing molecular dynamics, you're not gonna go into minutes, hours, because that will require a lot of time steps. Okay, and probably if I continue with the videos, I'm gonna explain why we use time step that goes into the picosecond range. Then we have to create a lattice. In this case, it's gonna be an FCC because it's copper. Okay, and here we define the lattice constant of copper that we got that from the internet from experiments, and then I create my lattice. So my lattice is gonna be 5 units X, 5 units Y, and 5 units Z. And then I had to define interatomic potential function right here. This is the one that I'm using. And then the first step that we had to do is an equilibration. So remember, we had to have the velocity. So in this case, I want all the particles, all the atoms that we had in copper to behave like a Maxwell-Boltzmann distribution. So that's the reason why. And I want all the velocities to have distribution is around 300 Kelvin. Okay. Then we go into the equilibration. So to the equilibration, I'm going to use the NPT because we have to have the temperature to be at 300 Kelvin. That's ambient temperature. And when we want to have the pressure to be equal to 1 atmosphere. Okay. So the reason why it's here convenient to use an NPT. Okay. Then I can look at my variables, the pressure, the volume, the temperature, and then I can run the simulation. Okay, having all these conditions. And based on that, I'm gonna obtain a crystal or a copper that is at 300 Kelvin. I have a pressure around 1 atmosphere. Okay. Then I'm gonna say that volume because I want to going to reduce units. Then I'm gonna do the following. Okay, I'm gonna increase the temperature of the copper. So for that case, I'm gonna use NPT. So, and why I'm using NPT, and this one we had to consider our simulations. Okay, we have copper. Okay, and then I want to increase the temperature slowly. I'm gonna go and increase the temperature. But what gonna happen to copper? Typically, copper is gonna expand. Okay, the volume is gonna increase. Okay, so as we increase the temperature, the volume of copper is gonna increase, it's gonna expand. The pressure is gonna remain the same, it's gonna be 1 atmosphere. So as we increase the temperature of the copper and we increase it up, 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 and up, there's gonna be a point when copper is gonna convert from solid to liquid, and that's what we consider a phase change. Okay, so copper goes from solid to liquid, and when that happens, typically the volume, the structure is going to remain constant during that time. Okay, and that's how we can predict that there have been a transition from solid to liquid. Okay, we can do that, we can see that in simulations. Here, if you remember in my presentation, I have this data here that explain to me how we have it from experiments, but we can predict that using molecular dynamics simulation. So the reason why I'm right here, I'm using NPT, and I want to have the temperature and the volume, okay? Because I want to see that as we increase the temperature of the copper, the volume is going to remain constant, and then the volume is going to increase again. So I have here my script, okay? And having this, I can run the simulation. So I'm going to go here, okay? And I can run this, and then I have to wait for the simulation to run. It's running. It's gonna take a while. Okay, here I'm not using a huge. I'm using a lattice that have few atoms actually, because that's enough for my simulation. But if you run with more atoms, that we use, the better to predict things. So it's running right now. So right now it's doing the equilibration. Okay, so you can see here how your output, so the temperature, pressure, volume. So you can see it running right here. Okay, so and here you can see the time steps, how the simulation is running. So we are waiting right now for this to finish. I'm waiting for this. Now it's running into increasing the temperature of the copper. So again, we have to wait for this to finish. We are waiting for this to finish. It's gonna take like 3 minutes, so it's not gonna take so long to finish this. This is when you go and you grab a cup of coffee and then you come back because it takes a while, you know? And usually when you're running computer simulation, we have millions of atoms, probably gonna take hours, probably gonna take days. So in that situation. You go, you grab your cup of coffee, and you wait. Okay, so right now I can see that I have, because I wanted to have an image for my crystal structure, in this case is copper, and I have two files. So I have the melting, this is the one I'm gonna use, because this one has the volume and the temperature. So if I go here, yes, and I run the simulation, I can see clearly this is and probably have to remove the lines. Then I can go and use the star. So you can see right here that the temperature is increasing, and right here in this temperature the volume remains the same, and then again continues uh, expanding. So right here we have the melting temperature that's around 1439 kelvins. Okay, so it's pretty much how I do my prediction. If I go here in the next slide, actually run this, the same image I have right here, so you can see that the melting temperature is around 1395 Kelvin, and this is not correctly. This is not accurate enough, but I gave you an idea. So you can go here and see that on experiment we have 1358. We got 1395 Kelvin, so it is really close. Okay. Now it can be between 1395 and it can be between 1500. Okay, so this is not a good way to do a prediction of the melting cup for an object, but at least it's an idea how to do a molecular dynamics simulation. Then if we go into the next slide, we actually can grab these images right here that we have for copper, and then we can just run a video how it's going to look like. So this is a lattice, and you can see how the arms are moving, and you can see that when it becomes a liquid, the volume expands abruptly. Okay, so that's when you know that you have phase transition, and you can see how the arms move. This is like a movie that you are making. Okay, grabbing all the images and making it into an animation. And yeah, that's pretty much what it says, and you can predict this curve right here, and this for what atmosphere using molecular dynamics simulations. I want to comment that there are many techniques. Probably I can go because I have here some reference that maybe you're gonna go and read right here. For example, I have this one right here. Molecular dynamics studies for melting copper with vacancies location at high pressure. So pretty much we have models that we use, okay, to predict the melting temperature as function of pressure. For example, right here we see it. Okay, so there are many ways to calculate the melting temperature of an object. I can give you, if you want, I can give you more references, okay, on how to do this, okay. But anyway, this is an example I want to show you. And I think that with this, I'm gonna end the presentation for today. Or let me see if I forgot something. Well, another reference that you want to study, probably reference to copper right here. This one an example, you know. There are different ways to find the melting point of materials. This one an example is not so accurate, but at least I give you an idea how to predict it. And yeah, it's pretty much an application that we use for molecular dynamics. Okay, if you have comments, okay, I'm gonna continue doing more videos about this. Depending on what people tell me, I can extend these videos, add more, you know. So please give me feedback and comments about this, and probably we can work on explaining this to people. So I'm gonna end the video for today, and thank you. And